A cracked rock on the side of the road should not contain crystals this clear. Not museum specimens, not deep mine discoveries, just geodes left behind because they looked ordinary. Inside some of them, transparent structures formed during interrupted growth cycles, layered chemistry shifts invisible from the surface, crystals normally associated with entirely different environments. Nothing on the outside suggests rarity until the stone is opened. Starting at number 10, a quartz formation that records the exact moment geological conditions suddenly changed. Ranked 10th, quartz scepter crystal, familiar object, unfamiliar interior. Geodes are often judged before they are opened. Weight, texture, surface pattern. These signals usually tell collectors what to expect inside. Most contain predictable quartz points formed through steady mineral deposition over long periods of stable geological conditions. Nothing dramatic, nothing unexpected. Yet occasionally a geode forms during a sequence of interruptions. Pressure fluctuates, fluid chemistry shifts, growth pauses, then resumes under slightly altered conditions. Instead of producing evenly shaped quartz crystals, the formation process leaves behind a structure that appears subtly out of place, a crystal with a narrower base supporting a wider secondary crown. This is known as a scepter crystal. At first glance, the difference seems small. The material remains quartz, one of the most familiar minerals found in geodes worldwide. But the geometry tells a more complex story. The lower crystal forms first, developing gradually as silica-rich fluid deposits microscopic layers along the cavity walls. Then something changes. Mineral supply slows or temporarily stops, leaving the crystal tip exposed to a different environment before growth begins again. When crystallization resumes, the new quartz does not continue at the same rate or pattern. Instead, it expands outward more rapidly than the original structure beneath it, forming a wider termination that sits atop the earlier crystal like a crown. A subtle shift in conditions produces a visible record of environmental change, preserved in crystal form. From the outside, the geode that contains such a structure rarely appears remarkable. Its exterior often shows the same rough texture, muted coloration, and familiar shape seen in countless roadside specimens that are picked up briefly, then left behind. No visible signal suggests anything uncommon inside. Yet once opened, the internal geometry reveals that crystal growth was not continuous, but episodic, influenced by interruptions rarely observable without cutting the stone. The rarity does not come from the mineral itself, but from the sequence of events required for the structure to form. A small pause in geological time, captured in silica. What appears to be a simple quartz cavity becomes evidence that even highly familiar environments can occasionally produce structures shaped by unusually precise timing. A reminder that some of the most interesting mineral formations are not defined by exotic chemistry, but by subtle changes in the conditions under which familiar materials are allowed to grow. And that even among geodes considered ordinary, a few contain quiet records of interruption, preserved long after the environment that created them has disappeared. Ranked 9th, Chalcedony phantom growth crystal, a structure that remembers its earlier shape. Before a crystal becomes visible, its first form often exists only as a surface, a boundary between mineral-rich fluid and open space, a moment where growth begins, then stops, then begins again. Inside certain roadside geodes, Chalcedony develops in layers so fine that individual crystal fibers cannot be distinguished without magnification. The structure appears smooth, almost featureless, forming soft, translucent walls that line the cavity interior. But under specific lighting, faint internal shapes begin to emerge, subtle geometric outlines suspended within the stone. Not inclusions, not fractures, but earlier growth surfaces preserved beneath later mineral deposition. These are known as phantom formations. They occur when mineralization pauses long enough for the exposed crystal surface to undergo slight chemical or structural change before growth resumes. Each interruption leaves behind a boundary, a faint internal contour that reflects the shape the crystal once had at an earlier stage of development. Unlike external crystal faces, these structures remain hidden within the material, visible only when light penetrates the chalcedony at the correct angle. The effect is quiet but unmistakable, a layered internal architecture that suggests the crystal did not grow in one continuous phase, but through multiple episodes of formation separated by environmental variation. Changes in temperature gradients, shifts in silica concentration, subtle fluctuations in fluid saturation levels. Each transition leaves a trace, creating a structure that appears to contain earlier versions of itself embedded within its final form. From the outside, the host geode offers little indication that such complexity exists inside. Weathered surfaces and muted coloration provide no visible signal of the layered history concealed within the translucent shell. Many specimens are collected casually, opened briefly, then set aside without detailed inspection. Only when illuminated carefully do the internal boundaries become apparent, delicate contours marking previous stages of crystal development. Phantom Chalcedony does not rely on dramatic color or unusual chemistry to distinguish itself. Its significance lies in the preservation of process rather than appearance, a crystal that quietly records its own earlier geometry, a structure shaped not only by what formed, but by what briefly stopped forming before continuing again. Evidence that even in environments considered stable, growth rarely follows a perfectly uninterrupted path, and that within stones often regarded as ordinary, traces of earlier states may remain preserved beneath the surface, visible only to those willing to look more closely. Ranked 8th, Optical calcite fragment cluster. Clarity that requires stability. Most cavities never maintain. Light normally passes through calcite with little resistance, but in rare cases, it does something more unusual. It splits. A single beam entering the crystal separates into two distinct paths, producing a doubling effect known as birefringence, an optical behavior historically studied for its ability to reveal hidden structure within transparent materials. For this effect to appear clearly, the crystal must form with minimal internal disruption. Even small variations in growth conditions can introduce fractures, distortions, or microscopic irregularities that scatter light and reduce transparency. Inside most roadside geodes, conditions fluctuate too frequently to allow calcite to develop with such optical precision. Fluid composition changes, temperature gradients shift. Growth surfaces experience minor interruptions. These variations typically produce calcite that appears cloudy or uneven, limiting its ability to transmit light cleanly. Yet occasionally a geode provides a protected environment stable enough for calcite crystals to develop with unusual internal order. The resulting fragments display a clarity that allows light to pass through in parallel paths, creating the subtle visual doubling effect characteristic of optically coherent calcite. The phenomenon does not depend on size. Even small fragments can exhibit strong birefringence when the internal lattice remains undisturbed during formation. From the exterior, nothing indicates that such structural precision exists within the cavity. The host rock often appears indistinguishable from surrounding stones scattered along exposed roadside outcrops. Weathering obscures surface detail. Fractures follow familiar patterns. No visual signal suggests the presence of crystals capable of manipulating light in a measurable way. Only after the cavity is opened, in the fragment examined under directional illumination, does the optical behavior become visible. Lines appear doubled, edges seem slightly displaced. Light reveals structural order in visible and opaque minerals. The rarity of such calcite formations does not come from chemical composition alone, but from the requirement that environmental conditions remain sufficiently stable for extended periods of crystallization, a narrow balance between mineral saturation and structural continuity, an environment quiet enough to allow the lattice to align without interruption. Within geodes often assumed to contain predictable mineral deposits, occasional cavities preserve evidence that even delicate optical structures can form when geological conditions remain momentarily consistent. A reminder that clarity is not simply the absence of impurity, but the result of uninterrupted growth within an environment that allows structure to organize without disturbance. Ranked 7th. Fluorite, zoned translucent crystal. Chemistry that changes faster than the crystal can adapt. Color inside a crystal is rarely applied all at once. Instead, it develops gradually, influenced by subtle variations in the chemistry of the fluids surrounding the growing structure. Trace elements enter the crystal lattice in small amounts, sometimes replacing atoms within the structure, sometimes altering the way light travels through the material. Fluorite is particularly sensitive to these changes. As the crystal forms, slight shifts in chemical concentration can influence how the lattice interacts with light. A small increase in certain trace elements may produce faint violet coloration. A reduction in those same elements may allow the crystal to appear nearly colorless. Other variations introduce pale greens or delicate blue tones. Rather than blending uniformly, these changes often remain separated within distinct layers. Inside some roadside geodes, fluorite develops with subtle zoning patterns, faint bands of color suspended within otherwise translucent crystal faces. These zones reflect moments when the chemistry of the mineralizing fluid shifted just enough to alter optical behavior, without interrupting crystal growth entirely. The result is not a dramatic change in structure, but a quiet internal record of environmental variation. When light enters the crystal from different angles, the zones become more visible. Areas that appear nearly transparent under direct illumination reveal faint color boundaries when viewed through transmitted light. Each band marks a period when chemical balance shifted slightly before returning toward earlier conditions. Unlike opaque minerals, translucent fluorite allows these internal variations to remain visible long after formation has ended. From the outside, the host geode often appears similar to many others found in roadside exposures. Surface weathering conceals the internal structure, offering little indication that subtle chemical transitions are preserved inside. Many such specimens are opened quickly, examined briefly, and considered typical. Yet under controlled lighting, the zoning becomes evident, not as decoration, but as a record of how sensitive crystal growth can be to small environmental changes. Fluorite does not require dramatic geological events to produce variation. Minor fluctuations in temperature, fluid composition, or mineral concentration are often sufficient to influence how light interacts with the developing crystal. A structure shaped not by a single condition, but by a sequence of slight adjustments occurring during growth. Within geodes often assumed to contain uniform mineral deposits, fluorite zoning demonstrates that even modest environmental variation can leave visible traces inside translucent crystal forms. A reminder that complexity does not always appear as dramatic contrast, but sometimes as delicate transitions preserved within the lattice itself. Ranked 6th, Hematoid quartz. When iron alters the way transparency behaves, impurities are often assumed to reduce clarity. In many minerals, the presence of foreign elements disrupts crystal growth, producing opacity or uneven coloration that obscures internal structure. Transparent crystals typically form when the environment remains chemically consistent, allowing the lattice to develop without interference. Yet iron behaves differently. Under certain conditions, microscopic iron oxide particles become suspended within silica-rich fluid during quartz formation. Instead of preventing crystal growth, these particles integrate into the developing structure without significantly distorting the lattice. The quartz remains translucent, but its interaction with light changes. Rather than appearing purely colorless, the crystal develops a warm internal glow caused by the scattering of light through fine distributions of iron oxide inclusions. The effect is subtle, a shift toward amber or soft reddish tones visible only when light penetrates the crystal from specific angles. Unlike surface staining, these inclusions are embedded within the quartz itself, distributed throughout the internal structure rather than concentrated on the exterior. Inside certain roadside geodes, hematoid quartz forms when iron-bearing fluids interact with silica during crystallization. The presence of iron must remain balanced. Too little produces no visible effect. Too much disrupts transparency entirely. Between these extremes lies a narrow range where the quartz remains structurally coherent while displaying internal coloration created by microscopic mineral inclusions. The host geode rarely provides visual indication that such conditions occurred during formation. Exterior surfaces appear similar to surrounding stones, weathered by exposure and often overlooked among more visually striking specimens. Only when the cavity is opened does the internal character become visible. translucent quartz that appears illuminated from within when exposed to directional light. The coloration is not uniform. Slight variations in inclusion density create areas where the internal glow intensifies or softens across different crystal faces, evidence that the distribution of iron-bearing fluid fluctuated as the crystal developed. Hematoid quartz demonstrates that the relationship between impurity and clarity is not always straightforward. Trace elements can influence the way light interacts with the crystal without eliminating transparency, a structure shaped by chemical presence rather than chemical absence. Within geodes commonly assumed to contain simple quartz deposits, occasional cavities preserve records of mineral interaction, subtle enough to remain unnoticed until examined under careful lighting. A reminder that what appears to be a minor variation in chemistry can influence optical behavior in ways not immediately visible from the exterior of the stone. Ranked fifth, honey calcite blade formation, geometry that develops only when growth favors one direction. Crystal growth rarely expands evenly in every direction. Inside confined cavities, mineral structures respond to pressure differences, available space, and the orientation of the crystal lattice itself. When environmental balance favors one crystallographic direction over others, the resulting structure begins to stretch, flatten, or extend in ways that differ from more symmetrical forms. Calcite is especially sensitive to these directional influences. Within certain roadside geodes, calcite develops not as blocky rhombohedral crystals, but as thin, elongated blades arranged in parallel layers. Each blade reflects a period when growth proceeded more rapidly along one axis, while expansion along other directions remained limited. The result is a series of translucent crystal sheets that appear stacked within the cavity, often displaying a soft honey coloration caused by trace elements interacting with the crystal lattice during formation. These structures require relatively stable conditions to maintain directional consistency. Even small disturbances in fluid chemistry or pressure can interrupt blade formation, causing crystals to revert toward more common shapes. When the environment remains balanced long enough, however, successive layers continue extending in alignment, producing delicate formations rarely preserved intact once exposed. Externally, the geode that contains such calcite typically shows no distinguishing features. Surface fractures and weathering patterns resemble many other stones found in similar geological settings. Nothing suggests that internally, growth followed a controlled directional pattern rather than forming more typical crystal habits. Only after the cavity is opened does the structure become visible. Thin, translucent blades reflecting light along smooth planar surfaces, revealing subtle variations in tone across different layers. The honey coloration does not result from strong pigmentation, but from minor trace elements distributed evenly enough to allow light transmission while slightly altering its spectral balance. Each blade marks a period during which growth conditions remain sufficiently consistent to maintain orientation without interruption, a quiet indication that the environment surrounding the forming crystal remains stable long enough for directional structure to persist. Honey calcite blade formations illustrate how even slight imbalances in growth dynamics can influence the geometry of a mineral without altering its chemical identity, a structure shaped by orientation rather than composition. Within geodes, often assumed to contain predictable crystal forms, occasional cavities preserve evidence that crystal architecture can respond to subtle environmental preferences, producing internal geometries that remain hidden until the stone is opened and examined closely. Ranked fourth, translucent barite rose formation, a mineral appearing where silica usually dominates. Most geodes follow a predictable mineral sequence. Silica-rich fluids circulate through cavities, gradually depositing quartz, chalcedony, or other related minerals along the interior surface. Over time, repeated cycles of mineral saturation create the familiar crystalline voids commonly associated with geodes found along exposed roadside formations. Barite rarely belongs to this sequence. Unlike silica-based minerals, barite forms in environments where barium-rich fluids interact with sulfate ions, producing tabular crystals that grow outward in layered arrangements. These structures often develop in sedimentary settings or hydrothermal veins, not typically within silica-dominant geode systems. Yet under certain conditions, Mineralizing fluids carrying dissolved barium can enter cavities already undergoing silica deposition. When this occurs, barite begins forming thin, plate-like crystals that radiate outward from a central point, producing formations known as barite roses. Inside some roadside geodes, these rosette structures develop in partially translucent form, allowing light to pass through the layered crystal blades. The geometry appears delicate yet organized, multiple flat crystal faces intersecting at consistent angles, creating a repeating radial pattern. The presence of barite introduces mineralogical contrast within an environment usually dominated by quartz family growth. Its formation suggests that fluid chemistry shifted significantly during the mineralization process, allowing barium-bearing solutions to enter the cavity at a specific stage of development. Externally, the host geode typically reveals no visible indication that such a transition occurred. Surface characteristics remain consistent with surrounding stones formed under similar geological conditions. Weathered exteriors offer little information about the complexity of mineral interactions preserved inside. Only when the cavity is opened does the barite structure become visible. Translucent crystal plates arranged in layered symmetry, reflecting light differently from the more common prismatic geometries found in quartz-dominant geodes. Each rosette records a period during which fluid composition diverged from the chemical balance typically associated with silica crystallization. A brief interval in which different mineral pathways became possible within the same confined space. Barite rose formations inside geodes illustrate how mineral systems are not always isolated, but can overlap when geological conditions allow multiple fluid compositions to interact within a single cavity, a structure shaped by chemical intersection rather than chemical uniformity. Within stones often assumed to follow predictable mineral patterns, occasional specimens preserve evidence that even established formation environments can host unexpected mineral associations when fluid pathways briefly introduce alternative elements into the crystallization process. Ranked third, Apophyllite translucent pyramid crystal, a geometry controlled by chemical precision rather than space. Some crystals reveal their identity through shape long before their composition is confirmed. Apophyllite belongs to a mineral group commonly associated with volcanic rock cavities, particularly within basalt formations where hydrothermal fluids circulate through cooling lava flows. These fluids introduce dissolved elements that crystallize gradually inside open spaces, often forming minerals from the zeolite family. Apophyllite develops differently. Rather than forming fibrous clusters or rounded aggregates, it grows as sharply defined pyramidal crystals, often appearing almost glass-like when conditions allow sufficient structural order to develop. The faces meet at precise angles, producing reflections that resemble cut facets despite the crystal forming entirely through natural processes. Such clarity requires chemical balance to remain unusually consistent during crystallization. Potassium, calcium, fluorine, and silica must remain available in stable proportions. Even minor fluctuations in temperature or fluid composition can interrupt the development of well-defined crystal faces, producing distorted or incomplete forms instead of the symmetrical pyramids associated with fully expressed apophyllite growth. Within certain roadside geodes formed in volcanic environments, apophyllite crystals appear suspended along cavity walls, occasionally reaching a level of translucency that allows light to pass through the crystal body before reflecting from internal surfaces. This optical softness differs from the sharp brilliance of quartz, producing a more diffuse interaction with light that emphasizes the geometric precision of the crystal structure. Externally, the host geode typically offers no indication that such mineral chemistry occurred within the cavity. Basalt weathering patterns often produce rounded nodules indistinguishable from countless others scattered across similar exposures. Surface inspection alone rarely reveals the presence of zeolite-associated minerals within the interior. Only after the geode is opened do the pyramidal crystal faces become visible, arranged in quiet symmetry along the inner surface. Each crystal reflects the balance of chemical availability at the time of formation, evidence that the hydrothermal environment remains sufficiently stable for ordered lattice growth to occur. Apophyllite demonstrates that crystal geometry can depend as much on chemical precision as on available space within the cavity. a structure shaped by the consistency of the mineralizing environment rather than the size of the void in which growth occurred. Within geodes, often assumed to contain familiar silica-based formations, occasional cavities preserve minerals more commonly associated with volcanic mineral systems, indicating that even ordinary roadside specimens may contain evidence of more complex geochemical conditions than their exterior suggests. Ranked second, Celestite termination cluster. Conditions so specific that even minor disturbance prevents formation. Not all crystals tolerate instability during growth. Some minerals require environmental conditions to remain narrowly balanced over extended periods, allowing delicate lattice structures to develop without disruption. Celestite belongs to this category, a strontium sulfate mineral whose transparency depends heavily on the consistency of the fluid environment in which crystallization occurs. Strontium must remain sufficiently concentrated in solution. Sulfate availability must remain stable. Temperature variation must remain limited enough to avoid structural disturbance. Even modest fluctuations can interrupt crystal development, producing fractured or opaque material instead of the translucent terminations associated with well-formed celestite clusters. Inside certain geodes, however, protected cavities create microenvironments where chemical balance remains undisturbed long enough for celestite crystals to develop with unusual clarity. The resulting structures often appear pale blue or nearly colorless, with soft translucence allowing light to pass through multiple crystal faces simultaneously. Terminations remain intact when growth proceeds gradually, producing sharply defined edges that intersect at consistent angles. Unlike minerals more tolerant of environmental variation, celestite rarely forms well-defined transparent clusters unless conditions remain stable throughout the crystallization period. Minor shifts in fluid saturation can cause rapid structural changes. Subtle pressure variations can influence how crystal faces develop. Changes in surrounding mineral concentration can disrupt lattice continuity. Within roadside geodes, these requirements are not often met long enough for large, intact celestite terminations to form. Most cavities contain minerals capable of adapting to environmental fluctuation. Celestite requires the opposite: persistence of narrow conditions across extended time. Externally, the geode containing such a cluster offers little indication that these chemical requirements were satisfied during formation. Surface weathering conceals internal variation, leaving the stone visually similar to surrounding specimens formed under comparable geological processes. Only when the cavity is opened do the translucent crystal terminations become visible, arranged in clustered geometry that reflects sustained stability during growth. The rarity does not arise solely from mineral composition, but from the requirement that multiple environmental variables remain aligned long enough for structure to develop without interruption. Celestite illustrates how certain minerals form only when geological conditions remain sufficiently consistent to allow crystal lattices to assemble gradually without disturbance, a structure shaped by chemical balance sustained across time. Within geodes often assumed to contain more adaptable minerals, occasional cavities preserve evidence that fragile crystal architectures can develop when environmental variability remains temporarily constrained within unusually narrow limits. In first place, Phenakite colorless microcrystal, rarity that exists without drawing attention to itself. Rarity is often associated with visual intensity, strong color, large size, immediate recognition. Phenakite challenges that expectation. Composed of beryllium silicate, phenakite forms under geological conditions that rarely occur within the confined environments typically associated with roadside geodes. The availability of beryllium must coincide with precise temperature ranges, compatible host rock chemistry, and sufficient structural stability to allow crystal development without interruption. Even when these conditions align, the resulting crystals often remain small, colorless, transparent, easily mistaken for quartz during initial inspection. Without detailed examination, phenakite can remain unnoticed among more familiar silica-based minerals. Its optical behavior lacks the strong coloration that often draws immediate attention, yet its crystallographic structure differs fundamentally from quartz, despite their visual similarity. The distinction lies in internal arrangement. Atomic structure influences how light travels through the crystal lattice, producing subtle differences in refractive behavior that require careful observation or measurement to identify reliably. Inside certain geodes formed within complex geological environments, phenakite microcrystals occasionally develop alongside more common minerals, reflecting localized availability of beryllium-bearing fluids during crystallization. Such conditions are uncommon, requiring geochemical pathways capable of introducing elements not typically associated with silica-dominant cavities. Externally, the geode offers no indication that these conditions occurred during formation. Surface characteristics remain consistent with surrounding stones shaped by similar weathering processes. Nothing suggests that trace quantities of beryllium were present during the mineralization sequence. Only when examined closely do the small transparent crystals become distinguishable from surrounding quartz points. A difference measured not by color or size, but by structural identity. Phenakite illustrates how rarity does not always announce itself through dramatic appearance. Sometimes it remains visually quiet, requiring analytical attention rather than immediate recognition. Within geodes commonly assumed to contain predictable mineral assemblages, occasional specimens preserve evidence that uncommon chemical environments can exist within otherwise familiar geological settings. A reminder that rarity is not always defined by how strongly something stands out, but sometimes by how easily it can remain unnoticed among what appears to be ordinary material. Geodes are often opened out of curiosity, but occasionally they reveal something more than expected. Not because the minerals are unfamiliar, but because the conditions that formed them were unusually precise. Short interruptions in growth, minor shifts in chemistry, brief windows of environmental stability. Each crystal preserves a moment when geological variables align just long enough to leave visible evidence inside otherwise ordinary stone. Nothing about the exterior suggests complexity. Nothing indicates rarity. Yet inside some of the most overlooked specimens, structures form that challenge assumptions about where certain crystals can develop. A reminder that rarity is not always hidden in remote locations or deep excavations. Sometimes it exists quietly, inside objects that appear predictable, and occasionally, what looks ordinary at first glance contains a structure that only becomes visible once the surface is open.